In this video, I'll be going over how we can prove triangles that are congruent using the side-side-side, side-angle-side, and hypotenuse-like theorem. So we first are starting with our definition of congruent, which we've seen before, but congruent means geometric figures that have exactly the same shape and same size. This means that all of the sides and all of the angles must be exactly the same to call them congruent. In congruent polygons, all parts of one polygon are congruent to all the corresponding parts of the other, so the angles and the sides. So we can use this knowledge to mark up these congruent figures and talk about what parts are actually congruent. So you can see the tick marks on the sides and then the arcs of the angles. For example, B and L in our two triangles here both have one arc, which means that angle B would be congruent to angle L. Similarly, angle A has two arcs, and angle M in the other triangle has two arcs. And lastly, angle C is congruent to angle N because those both have three arcs. So you're looking for the number of arcs to mark which ones are congruent. That means that if angle B was worth 65 degrees, then angle L would also be 65 degrees. Now similarly, we have our tick marks along the sides. And we can see that these both have one tick mark on A, B, and ML, but it's important on which order we write the sides based on the corresponding angles. So for example, if I want to call the first side side A, B, then I'm looking at the markings. A had two arcs and B had one, which means if I want to compare it to ML, I have to start with M because that also has two markings and it went with angle A. So we're going to put it in that specific order. We could have also said that BA is congruent to LM if you want to switch the order there. Again, with our tick marks, we look for the one that has two then, so I'm going to say AC is congruent to the one that has two tick marks on the other triangle, but from A to C, I'm going from two arcs to three arcs, so M to N in the other triangle. Our last congruent side would be BC, which is 1 to 3 arcs, so I'm starting with L going down to N. So these are all my congruent sides. Lastly, we can make like one final congruent statement here to mark that these two triangles are congruent to one another. Now, you have the flexibility of deciding what you want to call the first triangle. So if you want to just go in alphabetical order here, that's fine. ABC would be congruent to, and now this is where the order of the letters comes into play again. So since we started with the letter A is corresponding to M, which means we need to start our triangle name with M. The second letter we used was B, and that corresponds with L. And the third letter we used was C, which corresponds with N. So this is just one way that we can say that these two triangles are congruent. You could also say BAC is congruent to LMN, or many other combinations. As long as the order of the corresponding angles is in the right order, you can choose what you want. So we have an example below where it tells us that ABC, that triangle, is congruent to the triangle MNO. So something that I like to do is marking the angle or the vertex letters as certain colors to remind myself where we have corresponding parts in our triangle. So if that helps you, you can mark that on your notes. And once we have that, it kind of makes it a little bit easier to see what we're trying to solve for. So we've got a side called 32. That's our side AC. So I'm going to see that AC is congruent to another side. Well, AC was the yellow to the blue, so it would be yellow to blue on the other one, which is MO. That means that AC was 32, should be equal to whatever MO is called, which is the length of 5y minus 12. So we're going to have to solve this equation in order to get our answer here. So I'm going to add 12 to both sides. So I get 44 equals 5y. Divide by 5 on each side, and we end up with 8.8 equals y. So now that we know that 8.8 equals y, we can go ahead and use that to help us with the other part here, because they also give us that angle N is 90 degrees, and we know that angle N is congruent to angle B, which was given to us as 2x minus y. So I'm going to replace angle N with 90 and angle B with 2x minus y. But y we just solved for was 8.8, so I'm going to write my equation like that. We add 8.8 to both sides, so we're left with 98.8 equals 2x. We divide by 2 on each side, and we end up with 49 and 4/10 equals x. So that's how we can find our missing parts of a triangle, knowing which pieces are that the shapes are congruent and which angles and sides are corresponding and congruent to one another. So one of the theorems that we're going to use in some of our proofs coming up is called the third angle theorem. And that just states that if two triangles have two corresponding angles that are congruent, then the third angle of each triangle must be congruent to each other. So basically, if you were given these triangles and you were told, well, this is 65, and so is this one, and then maybe our other angle is 35, and so is the one that's corresponding to it, well, then we know that because triangles always have to add up to an interior amount of 180, that those last ones would both have to be 80, and that those would have the same angle measures in their triangles. That's called our third angle theorem. So some of the other postulates and theorems that we are using to prove triangles congruent. We first have what's called the side-side-side postulate, and we abbreviate this using SSS. So triangles can be proven congruent when all of the sides of one triangle are congruent to all of the sides of a second triangle. So if you were given a diagram like this, where all of the corresponding sides here were marked with those congruent tick marks, then you would be able to figure out what the congruent statement is, and the reason would be the side-side-side postulate. So we can make a statement, A to B is 1 tick mark to 2. B to C is 2 tick marks and 2 tick marks. So we want to check what order we want to put this in. So because I want to start with my side with 1, A goes to B, then E goes to F, B goes to C, F goes to D, and then C goes back to A, so D goes back to E. So that means the order that we write these triangles in is important. ABC would have to go with EFD. We couldn't say ABC is congruent to DEF. So just be careful of what order you're writing these in. And the reason for this would be because all of the sides were congruent. That makes the two triangles congruent to each other. Then we have our side angle side postulate, which is abbreviated as SAS. Triangles can be proven congruent when two sides and their included angle are congruent to two sides and their included angle of another triangle. So what we mean by that is if I had a triangle and I'm focused on this side and this side, well, this angle over here is not touching both of those sides that we're talking about, but the angle that's included would be the one that those two sides are making. So when we talk about included angle, it's between the two sides. So we can see in this diagram that A, B, and BC are making up this angle B that they are including there. So EF and D or FD are making up this angle F. That means that B and F are corresponding there and they're marked as congruent. We can also see that AB is congruent to EF and BC is congruent to FD. So we have two sides and an angle that are congruent, but they're in this specific order because we go from side to angle to side, and that's the included angle there. So this is our side angle side postulate. This is enough information for us to prove that these two triangles completely would be congruent to each other. Then we have our Hypotenuse-Like Theorem. This can only be used when we're talking about a right triangle, because a right triangle has hypotenuse, which is your longest side across from the right angle, and then the other two sides of a right triangle are called the legs. The Hypotenuse-Like Theorem states that if the hypotenuse and leg of one right triangle are congruent to the hypotenuse and leg of another right triangle, then the two right triangles are congruent. So, for example, in this drawing, we can see our right triangles are marked. When we look across from the right angle, that is called our hypotenuse. So this side right here is the hypotenuse. And we can see that the two hypotenuses of these triangles are both marked with two tick marks, which means they're congruent. Then we have another side that is on our triangle. Since it's not the hypotenuse, it's called the leg. The other side is also called a leg, but we can see that these two legs are marked as congruent to one another. And if we kind of turned this triangle to face the other way, like the other one is, we would have D, E, and F right here. So our hypotenuses were marked the same, and this longer leg were marked the same. So that means that we have an hypotenuse and a leg in a right triangle that are both congruent to one another. So we can say that triangle ABC is congruent to triangle EDF, putting them in that same order. So if it helps you to redraw it in the same orientation, that might help you name them. And then a question that we get sometimes is, why would the side-side angle not be a congruence postulate? Well, if you think about it, you could have a triangle that is not congruent because there's two possibilities. If I have this side congruent to this side, and this side that is congruent to this other side over here, and then there's just an angle that is not the included angle, well, then that means that this last side that we don't know about, AC on the bottom here, could be this long, or it could be this short on the second one. So because you're not dealing with that included angle, that's why the side-side angle would not be a postulate to tell us that these triangles are congruent, because it's not going to guarantee that that angle B or angle Q are going to be congruent to each other as well. So we need that included angle when we talk about the side angle side, and we would not have side-side angle as one of the reasons. So in this section, we are looking to decide whether these two triangles can be marked as congruent, and if they can be, we need to say why. So which postulate are we using to determine whether these are congruent? So I can see in this triangle that ABC is congruent to EFD. Well, we want to double check that the order looks right. DE and AC those are the first and the third letters, so those are congruent. And then AB are the first two, and EF are the first two, so those ones are congruent. And then we have BC and FD, which are the last two letters. So those are all in the corresponding places. They're all marked as congruent in the diagram, which means we can say, yes, these two triangles are congruent because of the side-side-side postulate. In the second one, we have ABC is congruent to CDA. So ABC goes from here to here to there. So then CDA would be this side to the middle. Well, we can see that these two triangles are sharing this middle piece. So that means that that piece, AC, has to be congruent to itself because it's the same piece of the shape. If they're both sitting on that same segment, then that segment has to be congruent to itself. And we call that the reflexive property. So because those are the same sides, and we already had that the other sides were marked as congruent to one another, these were isosceles triangles, then we can say that this is true because of the side-side-side postulate. We know that all three sides are congruent to each other, so that would be our reason. In the next diagram, we have ABC is congruent to EFD. So A to B to C, and then E to F to D. Those are marked the same way. Even though they're not facing the same way, we can see that they are in the right corresponding places. We have a congruent side. AB is congruent to DE. Angle A is congruent to angle E. And side AC is congruent to side EF. So we have two sides and their included angle that are marked as congruent, which means these two triangles would be congruent because of the side angle side postulate. Because those angles are right in between those congruent sides, that is allowed to be our side angle side. In the last one, we have two right angles marked right away. That should stand out at you that this is a right triangle. So we might be looking for hypotenuse leg. It could be a different reason though. So we want to check and see what we have true here. Well, we already know that these are both 90, so we have an angle that is congruent. We also have AC is congruent to BC. So we have the hypotenuses that are congruent. We know these are the hypotenuse because they're across from the right angle. So if it's going to be Hypotenuse-Leg Theorem, then we need a leg that's congruent. Well, we always want to mark shared sides, and we have this segment CD. It's congruent to itself based on their reflexive property. So this is a leg now. CD is one of the legs. It's congruent to the other leg of itself on the other triangle, and the hypotenuses are congruent. So these two triangles would be congruent based on the Hypotenuse-Leg Theorem. So now we're going to use all of these theorems and reasons in some proofs to determine whether or not triangles are congruent. So given that we have the segments AB is congruent to segment DB, So in the picture, that's this side and this side. And then we are also told that C is the midpoint of AD. So AD is down here. If C is that midpoint, then that would mean that these two pieces have to be congruent, because if C is the halfway point between those 2 points, then those two sections must be the same length. So we're going to use that to help us. We can also look for our shared side right away every time we have a proof like this. And we can see that BC would end up being congruent to itself because it is sharing that middle piece of the triangle. So we're going to fill in our proof. AB was congruent to DB was one of our given reasons. And then the second statement isn't there, but it says reflexive property. Well, we already marked up our triangles to kind of see this, and we saw that BC was the shared side between the two triangles. Reflexive will always be setting one side of one triangle equal to that same side, but on the second triangle. So it's that shared side. Then we have C as the midpoint of AD. That is given. And because of that, we know that AC has to be congruent to CD. And the reason for that is just the definition of midpoint, because we know that if you have a midpoint, then it breaks it up into two congruent sections. So we call it the definition of midpoint as our reason there. So finally, we can come to the conclusion that triangle ABC would be congruent to triangle DBC, and that's because we have three sides of these triangles that are congruent to one another. So this would be because of the side-side-side theorem. In our next proof, it is given to us that the segment SR is congruent to the segment PQ. So SR and PQ. Those are marked with the tick marks there. Then we are also told that SR and PQ are parallel. So remember, that's the arrows that are marked here. So the tick marks mean congruent, the arrows mean parallel. We're trying to prove that these two triangles are congruent to each other. So the first statement that SR and PQ are congruent was given. We're looking next at our second statement. It's blank, but the reason is reflexive property, so we're looking for a shared side in our diagram. Well, we can see that this middle side of this triangle, PR, would have to be a reflexive statement because it's being shared by both triangles. So PR is congruent to PR. Then we were given that SR is parallel to PQ. So if we know that now, so far what we've figured out is that we have two sides that are congruent to each other. We don't know anything about side SP or side QR. We don't have enough information to find those. The only thing that we could probably figure out at this point are some angles. So if I want to use the side angle side postulate that we learned about angles and sides relating to each other, I would need this angle that is shared, or that is the included angle between PR and RS. I would also need to know something about the angle between PR and PQ. So those angles, in comparison to each other, they're on opposite sides of the line PR, and they're inside of these parallel lines. So you can kind of think back to our parallel lines unit. Imagine that this was two sets of parallel lines rather than just the segments, and we had this transversal going through them. Well, we have those two angles, RPQ and PRS, that are inside the parallel lines and on opposite sides of the transversal. So that means that those two angles have to be congruent. SRP would be congruent to angle RPQ. This is true because these are alternate interior angles. So the alternate interior angles theorem tells us that those two must be congruent because their lines were parallel. So now that we've come to that conclusion, we have enough information to say that we have two sides that are congruent and their included angle, which means that by the side angle side theorem, these two triangles would be congruent to one another. So if you are given parallel lines, we still have to use those angle pairs that we learned already and apply them to these triangles now. In our last proof, we are given that side AB is congruent to side AC, and that BC, so the bottom right here, is perpendicular to AD. That's what that symbol means, perpendicular. Remember that perpendicular lines make 90-degree angles. So that means that we can mark right away that this would be 90 degrees and so would this angle. So we're going to start filling in our proof here. AB is congruent to AC was given, and then the next statement was blank, and we're told it's the reason because it's given, so BC was perpendicular to AD. So they're telling us that angle ADB and ADC are right angles. Well, we know that's because of the definition of perpendicular lines. So since we were told that those lines are perpendicular, we can use their definition to make those right angles. Then we have a blank space here for our statement and our reason. So we want to look at our picture and see, well, how could we maybe start trying to prove these two triangles congruent? I have a right triangle, and I can see that the angle, or the side across from the right angle, is marked as being congruent. Well, remember that the side across from the right angle is always the hypotenuse. So right now we have two hypotenuses that are congruent to each other. So if we want to use Hypotenuse-Leg Theorem, we would need to know another leg that is congruent to another leg in the other triangle. So we actually can use the reflexive property here because AD would have to be congruent to itself because it's that same section of the line. So since AD must be congruent to AD, that's because of reflexive property. Now we have enough information to say that these two triangles are congruent because of the Hypotenuse-Like Theorem. I have a leg and a hypotenuse from a right triangle, two right triangles that are congruent to each other, which makes those triangles congruent to one another.